Okay, topic 4, experimental errors and data analysis. First question, which of the following is an example for a systematic error? Random fluctuations. The moment there is a name called as random, this definitely cannot be a systematic error. In a room temperature doing an experiment, this is incorrect. Consistently reading a scale from an angle causing a parallax, right? So for example, some of them might have an habit of looking at it like this over here. So if this is the pen over here and I'm going to measure the length over here, ruler, so what I do is I can look from it here from the top, and every time I make a mistake, so the same parallax error will get counted. So there is a possibility or B should be your right answer. Let us look at the rest of them also. Variations in reaction time, okay, when using a stopwatch. So reaction time, okay, can change because it's already, so it will be around 0.3 seconds, 0.1 seconds, 0.2 seconds and so on. So this will be a random error. So you cannot consider this. Different results obtained when repeating the same measurement. Okay, different results obtained. For example, you get 9.8 ones, 9.7 ones, 9.4 ones, 9.1 ones, maybe 10.3 ones. Okay, so that could be because of a random error. This is in calculation for the acceleration due to gravity. Okay, so this can be due to random error. So definitely this is also not the right answer. B should be your right answer. Then a student measures the period of one pendulum by timing 20 oscillations and dividing by 20. So you calculate the value of time period by using 20 oscillations, time taken for 20 oscillations, and divide this by 20. Okay. Which of the following would reduce the percentage uncertainty in the measurement? You need to reduce the percentage uncertainty, right? So using a pendulum with a heavier bob. See, time period does not depend upon the heavier bob. So therefore, the mass of the bob actually, the time period only depends upon the length, which is given by the formula 2 pi into root of L by G. So either it depends on the value of G, because you are using the same place. I am not going to consider the effect of G. It's only the value of L. Okay, so it directly is proportional to root L. Okay, now, so therefore, using a heavier bob will not change anything. So therefore, this is incorrect. Timing 50 oscillations instead of 20. Now let us understand what is the question here. It is percentage uncertainty. What is percentage uncertainty in time period? This should be delta capital T by small capital T over here, right? So delta T by T over here. So therefore, if this, when can this percentage uncertainty multiplied by 100? When can this value be smaller? It can be smaller. Whether the delta T should be smaller or this capital T should be larger over here. Okay. So therefore, now if I say I am timing 50 oscillations instead of 20, then what happens is this time taken for it will also become increasing. Okay, and what will happen? So we are going to have 50 oscillations. So definitely, if this increases, and as a result of it, delta T by T will reduce over here, right? Therefore, this could be your right answer. Next is using a pendulum with a longer string. So T is equal to 2 pi root of L by G. Of course, this will also reduce it because time period is going to increase based on this. But you know, since the time period increases, but the effect that you observe here will not be seen over here. It will be much lesser. So comparing these two, I think B should be your right answer. Okay. Otherwise, C should be also be equally the same. Okay. Then taking the average of two measurements of 10 oscillations each. This is definitely incorrect. So therefore, B is the right answer. Then a diagram shows a graph with error bars. What can be concluded from this data? Since I can't include a direct image, I describe it. Okay, so I have written some note over here because I was not able to put the image. So a graph, okay, the image looks like this actually. A graph showing a linear trend. So you will get a graph of y versus x like this over here, and the graph was something like this over here. So you get 1 point here, 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 and so on. So when I drew this graph, it was either going like this, or maybe if I consider these points, you would have got a graph like this over here. Okay, so therefore this was a little bit confusing, and I think I did not have the space, or maybe I was not able to copy the graph. Okay, so that's why I did not put it across here. Now let us read this. Okay, this is the kind of graph that you get over here. The data strongly supports a linear relationship. It does not support a linear relationship. The reason is because some points are missing from the graph. Either if I choose this graph or this graph, 1 or 2 points are missing. So definitely it is not supporting this. So A is incorrect. Data disproves a linear relationship. It does not prove a linear relationship. Okay, it disproves a linear relationship. B is definitely right. The error bars are too small to draw any conclusion. No, there are some error bars being observed, but unfortunately, all the points There's a straight line does not pass through all the error paths. So this is incorrect. The relationship is likely exponential than linear. See, if I had shown you a graph like this, then you can say this is exponential. But of course, it is not like this. The graph is shown like this. Maybe if I had shown you the graph over here, you can conclude it in a better way. Okay, now let me move on to the next one. Fourth question. Which of the following would help reduce random errors in an experiment? How do you reduce the random errors? Calibrating the measurements instruments before use. Okay, this will not reduce the random error. Systematic error can be reduced using this method. So this is an incorrect answer. Taking multiple readings and calculating the mean. This will definitely reduce it. See, the reason for doing more than one trial or 3 trials or 5 trials and so on, okay, even in your IA or E or whatever it is, it's only because to reduce the random error. Okay, so this will definitely help you. Ensuring the experiment is conducted at a constant temperature. No. Okay, so whatever you do, because certain experiments need not conduct at a constant temperature. So therefore, this is not the right one over here. Using a different measuring technique altogether. No. So if there is a random error, because maybe because of the human error, okay, you cannot avoid it. So therefore, this is also incorrect. So B should be your right answer. Next. According to Heisenberg's uncertainty principle, if the uncertainty in the position of a particle decreases, so if your delta x decreases, what happens to the uncertainty in the momentum? What happens to delta p? So therefore, we know that delta p into delta x is equal to h cross, which is your uncertainty principle. So I can now write delta p is equal to h cross divided by delta x. If this delta x reduces, then automatically delta p will increase over here. So therefore, it increases. So where is it? It increases. B is the right answer. So with this, I think we have come to an end to all the 5 questions in this chapter. So all these questions, the worksheets, if you want to download, is already available in my website. You can look into this link over here. Okay, so you can go to Unit A, which is for concept-wise questions. You can either click onto this, or maybe you can visit my website, and from the website, actually, you can go there.